All right, let's talk about triangle angle sums. Triangle angle sums, sort of a mouthful. What are we talking about? Well, we're talking about adding up certain angles inside triangles. Okay, sums, of course, is the answer to an addition problem, and angles inside triangles. Let me just mention some texts call this process, they refer to this as triangle sums, which I think is somewhat misleading. We're not adding triangles here. We're adding angles inside of a single triangle to each other. So triangle angle sums. Before we get into it, we need to cover just a couple vocabulary words. The first angle we need to be aware of is called an interior angle. An interior angle is an angle formed inside a polygon by two adjacent sides. Notice that the definition is true for any polygon, even though we'll be focusing on triangles. So, for example, suppose I have this triangle, and I want to talk about this angle, angle 1. We'd say that that's an interior angle. It's inside the polygon, it's formed by two adjacent sides. If we were talking about a quadrilateral, and I want to talk about this angle, angle 3, that's also an interior angle in this quadrilateral, because it's formed by two adjacent sides. So an interior angle is an angle formed inside a polygon by two adjacent sides, no matter what kind of a polygon, no matter how many sides it has. This would be a good time to review really quick how we name polygons, by the way. We name polygons by assigning names to their vertices, and then we simply list the vertices in order. It doesn't matter where you start. So for instance, this triangle could be called triangle ABC. This quadrilateral could be called quadrilateral DGFE. That's fine. As long as you start at one vertex and name the others consecutively. That's how we name polygons. Okay, let's look at an exterior angle. An exterior angle is an angle formed outside a polygon by a side and the extension of an adjacent side. That's a little less obvious than the interior angle. Let's just take a look at it. We'll look at another triangle, although this could be done in any kind of polygon. The interior angles are very obvious, but where are the exterior angles? In order to find the exterior angles, we need to extend one of the sides. So for instance, suppose we extend this side. We'll call that side AB. Side AB. We extend side AB, and here's one exterior angle right here. That's an exterior angle. Okay? There are actually 6 exterior angles in every triangle, because at each vertex on the outside, we could extend either side and then find another angle. We could extend side BC or AC, and in either case we'd find another angle. And of course we could extend side AC in this direction and side BA in this direction, and we'd find that we have 2 more exterior angles here. Notice that as I've marked these angles, my primary purpose was just to draw your attention to the angle itself. But I've used varying number of arcs. And you'll notice when I drew these 2 exterior angles, I marked them with the same number of arcs because they're congruent. How do we know they're congruent? By the vertical angles theorem. Hopefully that was coming into your mind as you watched this. So these are congruent by the vertical angles theorem, these are congruent by the vertical angles theorem, and these are congruent to the vertical angles theorem. Notice that they could all have different measures. There's no reason to suspect that they're the same. In fact, they certainly don't look the same. But those are exterior angles. Angles formed outside a polygon by a side and the extension of an adjacent side. So we have interior and exterior angles, and now we're going to talk about some of the sums that we see occurring in triangles. The triangle angle sum theorem, which is the first one we need to look at, says that the sum of the measures of the interior angles of a triangle is equal to 180 degrees. So no matter what triangle I'm looking at, I know that if I add up all 3 of the interior angles, the sum will always be 180. Let's see if we can prove this rule now. I have triangle ABC here, and you'll notice I haven't put any numbers in here. I don't know any of the measures of the triangle, and that's important. Remember, we always try to prove theorems in the general, and then apply them to the specific. We never prove them in a specific case, and then attempt to apply the specific example to the general. That will never work very well, at least not reliably. So here we have triangle ABC. I'd like to try and prove that the measures of these 3 angles add up to 180. Here's how I'll do it. In a prior section, you may have learned that with every line and a point not on the line, there is a single second line that goes through that point that's parallel to the first given line. Here's what I mean by that. There is some line that exists that is parallel to line AB and passes through point C, the vertex. And as soon as I've drawn that line in there, you can now see that I have two parallel lines, and I've also have two transversals. So we're going to look at one of them in turn. To make this whole process a little bit easier, I'm just going to label these 1, 2, and 3. For starters, I think we can all agree that the sum of the measures of angles 1, 2, and 3 is 180 degrees. And that is by the angle addition postulate. We can see we have a straight angle across by vertex C, and so 1, 2, and 3 add up to 180. So that's pretty unremarkable. But now, because we have these transversals in here, we can also conclude that the measure of angle 1 is equal to the measure of angle 4. And the measure of angle 3 is equal to the measure of angle 5. And both of those are by the alternate interior angles theorem, just applied on two different transversals, transversal AC and transversal BC. So by substitution, since the measure of angle 1 equals the measure of angle 4, and the measure of angle 3 is equal to the measure of angle 5, we can make a substitution and conclude that the measure of angle 4 plus the measure of angle 2 plus the measure of angle 5 is equal to 180 degrees. And so we've actually proven it. This is somewhat of an informal proof. I haven't taken the time to walk through it every step formally, but I think you can see that it's reliable, and we've proven that the sum of the measures of the interior angles of a triangle is equal to 180 degrees. I'd like to show you one other demonstration that will help you to see that this is true. And to do that, I have this paper triangle. You can try this at home. I'll be using a specific triangle to show you that this rule works. But remember that this is not the best way to prove anything, because when I reason through a proof this way in the general, I'm using deductive reasoning to prove that this will work every time. When I use a specific triangle that I happen to have in my hand, I'll be reasoning by inference. That is, assuming that this pattern continues on, I can conclude that it's reliable. But the problem is, of course, with reasoning with patterns, sometimes they break down. So, anyway, having said that, all I'm going to do is I'll just tear the corners off of this triangle. And so now, in sort of a strange sense, I can move these corners around the vertices. And you'll notice that if I arrange them vertex to vertex, they appear to form a straight line across the top. Okay? Now, if you think that the triangle I'm holding is just some sort of a trick triangle and I happen to measure its angles perfectly so it would do that, why don't you try it at home? Just cut out a triangle, tear off its corners, and see if the corners form a nice straight line. I think you'll find that they do. Okay? And in fact, they ought to, or else geometry will crumble. Because we have this thing called the triangle angle sum theorem, and a deductive proof which says this must be true every single time. That's the triangle angle sum theorem. Let's look at a couple examples of how we can use the triangle interior angle sum theorem. Suppose we have a triangle with the following measures in the interior angles. Suppose this is 80 degrees. And let's suppose that this one up here is 70 degrees. And the question is, what is the measure of that angle there? What's the measure of this angle here? Perhaps we need to know it for some particular reason, some calculation related to something that's going on elsewhere in the problem. How can we find it? Well, all we need to know is that the sum of the interior angles is 180. Therefore, 80 plus 70 plus x is equal to 180 degrees. We can simplify the left side. 150 plus x equals 180. And by the addition property of equality, subtract 150 from each side. We know that x equals 30. Okay, x equals 30. And so you can see we can use this property, the fact that the interior angles of a triangle always add up to 180 degrees, to always find the third angle anytime we know two of them. Let's try one more that might not be quite as obvious. Suppose we have something like this. X degrees, and 50 degrees. Again, we know that the sum of these three values is equal to 180, so let's just go ahead and add them up and see what we get. 50 plus x is equal to 180. We can subtract 50 from both sides. And we have x plus x is equal to 130. And then, of course, x plus x is 2x. And therefore, x equals 65. The next rule we need to talk about is the exterior angle sum theorem. Notice the name of it doesn't have the word triangle in it, and that's because this theorem actually works for any polygon. Doesn't matter how many sides it has, this theorem will work just fine. So I'm going to prove the theorem in the context of a triangle, but then we'll take a look at this quadrilateral here, which is actually a rectangle, just to see if it makes sense in that particular context. But the rule works on any polygon. Let me just note quickly here, it's important for me to just mention that we study triangles because they are the most basic polygon that exists. 3 sides, it's the minimum number of sides that a polygon can have. So that's where we begin our study, and we are going to spend quite a bit of time looking at triangles, to the point where it's going to start to get a little bit old, just being honest. But the good news is that triangles will be able to tell us a lot of information about other shapes when we begin to study those, and that's the reason why we start with triangles. They are the foundation of our understanding of spatial reasoning and the structures and components of other shapes that are slightly more complex. So we'll start with triangles. Let's take a look at this rule. Exterior angle sum theorem says the sum of the measures of the exterior angles, one at each vertex of a polygon, is equal to 360. This little piece in here, why is that in there? Remember, every vertex of every polygon has 2 exterior angles, and the exterior angles are always congruent. That is, the 2 exterior angles located at a single vertex are congruent. So when we talk about the exterior angle sum theorem, we only talk about 1 at each vertex. Let me just take a quick peek at that. For example, suppose we're looking at this triangle here, and we extend the sides in order to identify all of the exterior angles. I have an exterior angle here and here, those are congruent. Here and here, those 2 are congruent. And here and there, those 2 are congruent. So when we apply the exterior angle sum theorem, we're only talking about 1 exterior angle from each vertex. And the sum of those 3, in this instance, since it's a triangle, is equal to 360 degrees. Okay, now let's go ahead and prove this theorem. That is, prove the exterior angle sum theorem. For starters, we'll apply the triangle angle sum theorem, which says that the measures of angle 1, 2, and 3 add up to 180. The next thing we notice is that each of these angle pairs, 1, 4, 2, 6, 3, 5, is a linear pair. And so we can conclude that the sum of those angle pairs is equal to 180. So we have these 3 statements. Now, what we can do is we're able to solve each of these equations for the respective measures. I can solve this first equation for the measure of angle 1 by subtracting the measure of angle 4 from each side. And I can do that for each of these in turn. And so now we have these 3 statements. The measure of angle 1 equals 180 minus the measure of angle 4. The measure of angle 2, 180 minus the measure of angle 6. The measure of angle 3 equals 180 minus the measure of angle 5. And now we can make a substitution into this equation up here. I can plug this expression in for this expression in for the measure of angle 2, and this expression in for the measure of angle 3. We end up with the following. 180 minus the measure of angle 4 plus 180 minus the measure of angle 6 plus 180 minus the measure of angle 5 equals 180. Now we can simplify this left by combining the 180s and combining the angle measures, and we end up with the following expression. 3 times 180 minus the measure of angle 4 plus the measure of angle 5 plus the measure of angle 6 equals 180. Okay, the next thing we need to do is subtract 3 times 180 from each side. We now have, on the left side, negative measure of angle 4 plus measure of angle 5 plus measure of angle 6 equals negative 360. Multiply both sides by negative 1. And we end up with the sum of the exterior angles, 1 at each vertex, 4, 5, and 6, is equal to 360 degrees. There's the proof of the theorem. Let's just look at this example really quick, just to see if we can sort of intuitively think through it. I'll just draw 1 exterior angle at each vertex. And without doing a whole lot of heavy lifting, I think we can see that we have a 90-degree angle here, and here, and here, and there, 1 at each vertex. 90 times 4 is 360, and so the theorem holds up fine just there as well. Let's just look at one quick application, one quick problem. Suppose this problem is given to us and we're asked to find x. How do we do it? Well, we start by recognizing that these are exterior angles of this triangle, and we know that the sum of the exterior angles, 1 at each vertex, is equal to 360. Therefore, we know that 130 plus 120 plus x equals 360. And now we just need to solve for x. So this is 250 plus x is equal to 360. And we end up with x is equal to 110. X is equal to 110. So that's our answer for x. Pretty straightforward application. Let's look at one more problem. Suppose we had something like this. We have a triangle. We have two exterior angles that are unknown. And we have a third exterior angle that is known. Notice that these are the same measure. So let's just write it out in an algebraic expression. X plus 140 equals 360. The sum of the exterior angles is equal to 360. This is 2x. Subtract 140 from each side. 2x equals 220. Divide by 2, divide by 2. X equals 110. We find the answer that way. So sometimes we have algebraic problems, we need to do a little bit more work on them. But you can see the rule functions the same way. The sum of these three exterior angles, one at each vertex, is always equal to 360. Okay, the next rule we need to talk about is the remote interior angles theorem. And before we can talk about the rule, we need to define what remote interior angles are. Let's talk about those words one at a time. Remote just means far away. So if you use the TV remote, for instance, you're operating the TV from a distance. So remote just means far away, a remote desert island. Interior, of course, we know that means inside of a triangle. And angles, well, we know what angles are. So hopefully that's not too much of a stretch. But what is a remote interior angle? Let's look at it. When I'm focusing on a particular exterior angle, for instance, let's look at this angle number 1 right here. The remote interior angles are the two angles that are not adjacent to it. So in this instance, angles 2 and 3 are the remote interior angles from angle 1. Okay? If, however, I shift my attention from angle 1 to angle 4 over here, well, now 2 and 3 are no longer the remote interior angles. 3 is a remote interior angle from 4, but not 2. So I need to talk about 3 and 5 as being the remote interior angles. Remote interior angles are the interior angles which are not adjacent to the exterior angle under consideration. All right, let's talk about the theorem. Remote interior angles theorem says, the measure of each exterior angle of a triangle is equal to the sum of the corresponding remote interior angles. What that means is that in this instance here, we have a triangle, we have an exterior angle, and we've identified the two remote interior angles. It means that the measure of angle 3 must be equal to the measure of angle 1 plus the measure of angle 2. The measure of angle 3 is equal to the measure of angle 1 plus the measure of angle 2. Let's just do a proof, make sure that that holds up. Okay, in order to work through this proof, let's just get out some information that we're certain about in this particular triangle. First of all, we're sure that the measures of angle 1, 2, and 4 add up to 180 degrees. That's a triangle angle sum theorem. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 4, equals 180 degrees. We also know that the measure of angle 4 plus the measure of angle 3 is equal to 180 by the linear pair postulate. The measure of angle 4 plus the measure of angle 3 equals 180 degrees. You can see that the expressions on the left, if I wouldn't erase them, you can see them. You can see that the expressions on the left are both set equal to 180. So by the transitive property, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 4 is equal to the measure of angle 4 plus the measure of angle 3. You can also see, at this point, we can subtract the measure of angle 4 from each side. And so this cancels, and that cancels. And we're left with the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 3. And there's our theorem, that the measure of an exterior angle of a triangle is equal to the sum of the two corresponding remote interior angles. Let's look at a couple examples. Okay, a few examples here. 3 different triangles. We need to find the variables in each one. Let's start with this one up here. It's probably the easiest one. By the remote interior angles theorem, we know that the measure of 118 degrees is equal to the sum of x and 78 degrees and 78 degrees. So we'll just write that equation out. X plus 78 equals 118. And we need to solve for x by subtracting 78 from each side. And so we end up with x equals 40. X equals 40. Let's look at this one. Here, same exact rule. We have an exterior angle and two remote interior angles. So we know that y is equal to 120 plus 30. And therefore y equals 150. This one here is a little bit trickier. We have variables inside, 2x and x, and we know that this is 90 degrees here. So we write the problem first, get the geometry out of the way. 2x plus x equals 90. Now we can deal with the algebra. 2x plus x is 3x. Therefore x divided by 3 on each side, x equals 30. If we were asked a different but related question, what are the measures of these angles? Well, we would know that this angle is 30 degrees and this angle is twice that amount, or 60 degrees. All right, those are the rules we need to know about triangle angle sums. Make sure you find a few practice problems. And as always, if you have any questions, shoot me an email.